Okay, David Malin, CS50. This is the end of week 6. So hopefully that little Seinfeld clip made the creepy photo that some of you have recovered a little more sensible. Let's look back now at where we left off on Wednesday. So on Wednesday, we were talking about these linked list structures. One reminder, incidentally, about next Wednesday, which will be quiz 1. You should have all the requisite information for that already. So we were talking about storing ints in this so-called linked list structure. And this, I have to say, is remarkable. We have no one sitting in the aisles yet or standing in back. And yet we have so many free seats. So do say hello to all your friends for us later today if you could. So here we were with this linked list structure. So we were storing, recall, this linked list structure using one of these things. So quite literally a struct. And the first such version we looked at was in list1.h. And it was pretty simple. So we had this definition of a struct that had an int inside of it, which was our number, and then a pointer to another such node, as we called it. And so pictorially, it sort of looked like this thing. And we were connecting each of these ints together. So there's this sort of inelegance about this kind of data structure for a couple of reasons. One, we're sort of mixing the notion of the data that we want to store with this notion of metadata. The fact that we have a pointer in here sort of clouds the idea that all we ultimately want is a list of numbers. There's also this issue here, too, where we did a lot of work, or at least I did a lot of work, coding up list1.c. And unfortunately, the only thing this code is good for currently is storing lists of numbers. And yet it's quite reasonable to want to implement a linked list for other data structures altogether. But as is, if I wanted to, for instance, store a linked list of floating point numbers for whatever reason, maybe I'm implementing a program that's supposed to store a list of students' grades for which we actually want floating point values, well, how could I go about using this same program for floats or doubles? What's it going to take? Yeah? Oh, your hand's touching your face. I'll take that today. OK, so we could change the structure, right? I could go in with my text editor, do a proverbial find and replace, and just change pretty much all instances of int to float. I can recompile and then re-execute this program, and voila, I have a program now for doubles or floats. But now I change my mind. Now I want to store not ints, not floats, but strings. Now I have to go in yet again and sort of change the code to accommodate that design. So this code, as is, seems to be far from this notion of a library. And a library typically is some sort of set of code that's sort of reusable in different contexts. It's flexible. It's versatile. This code certainly is not. It's been designed right now. It's been hard-coded for just integers. Well, fortunately, we can do better. And you can do better without all that much more work. So in list2.h, I took a slightly more sophisticated approach to this same idea, but I factored out the piece of data that I actually wanted to store. And this isn't the perfect solution just yet, but it is one step closer. So in this example, for which you also have source code from Wednesday for reference, I wanted to store not ints, but student objects, because a student is a little more interesting in that it has multiple data associated with it. Arbitrarily, an ID, a name, and a house, each of which, notice, is of a possibly different data type. So fortunately, the linked list code is almost identical. So this stuff down here remains almost the same in that I'm storing still a pointer to some other such node, but instead of storing, obviously, an int n, I'm instead storing now a pointer to a student object. And what this allows me to have is a sort of layer of indirection. So I'm not storing all of my data inside the node itself, but I'm just storing a pointer to an actual struct that contains that data. And the only thing that this really changes that's worthy of note for now is some of the syntax here. So I'm going to fast forward through this program, which I do invite you, if not urge you, to look at your leisure at some point, certainly before problem set 5. And notice that in my traverse function for student objects, things are ever so slightly different. So here again, I'm just printing out the list is now. And now I'm initializing this temporary variable called pointer to be the front of the list, the first element. And now I'm about to say the following. While pointer is not null, I want to, on each line of my output, say that string of string, and then in parentheses, number sign. So what I want this program to do is look like this. So this is make list2. So I'm going to run list2. It's going to ask me to, let's say, insert. Student ID will be 1. David Mather, And that's the kind of output I want when traverse gets called. If I add just one more student, I might say student number 2, his name is John, and he's in Quincy House. And so all my traverse function is doing is just printing out the list of students in this linked list for now. OK, so with that in mind, let's go back to the actual implementation and notice the one piece of new syntax here. Because my data structure doesn't now look like this, but instead visually looks like this, where here's the linked list, but here now are the data that are actually being stored effectively in that list. What I now need to do is follow one pointer and then another pointer. And fortunately, the syntax is pretty intuitive. We go, if we want to print out the student's name, well, we start at the node in which we're in, according to PTR. We follow the student pointer, which leads us there. And then we follow the pointer to name so that we can actually reach the name value. And the end result, ultimately, is that we're printing out the David of Mather and then his particular ID number. And again, we're doing this flush thing to actually flush standard output. But we can do one step even better. And actually, let me think for just one moment here. So we're following that. OK, good. So we can do one step better in general, even though we don't have an example of this just yet for you, because we're not actually implementing a library yet, but rather we're just implementing the student example. It turns out in C that if we wanted to generalize this library further, there's still this problem right now that still, even though we have this layer of indirection and we have this ability now to store multiple pieces of data in our data structure in this linked list, we can still only store what types of data? Student objects, right, as that definition suggests. So it turns out in C that you can actually do this, though you won't see this that often in this course. You can have what's called a void star, which is a terribly generic pointer that can point to anything that you actually want it to. And with that feature of C, you have this versatility to begin storing most anything you want within a data structure of your own design. The only catch is that you very often then within your code have to do what in order to tell the compiler what you're actually pointing at? So you're going to have to come back to this idea of casting. So it does add a bit of complexity in that you have to yourself sometimes explicitly say what you're pointing to so that the compiler knows what the memory actually looks like that you're pointing at. But at least you have this ability to genericize data structures potentially in this way. So tuck that away for now as a potential feature of C. For those of you familiar with Java, you may recall that there's this class in Java called the object class that's very similar in spirit to this. It's a very generic object. So those of you coming out of AP Computer Science. But for now, the takeaway is just that we can have this layer of indirection and store things slightly more interesting than ints, and particularly multiple such pieces of data within our data structure. But it really depends on our goal. So problem set 5, which won't be distributed until next week, is going to task you again with implementing the fastest dictionary possible. And what does that mean? Well, we're going to provide you with a good amount of code that provides you essentially with a testing framework. But we, the staff, are going to stop short of implementing at least 2 functions. 1, load dictionary, and 2, isWord. So the first of those functions, goals, is to load a dictionary files like some of the hacker students used in problem set 2's crypto that contains 100 to 200,000 English words. And your task for the standard and hacker editions likely will be to load all thousands of those words into memory somehow, but presumably somehow efficiently, using perhaps some of the data structures we talk about today. isWord, quite simply, just needs to return true or false. But you've got to do this as quickly as possible. So you might imagine that you could store a dictionary in memory using a linked list, right? Better yet, you could sort it, or maybe you could even use an array so that you could binary search it. The problem, though, is that when you start talking about 100,000 words or 200,000 words, iterating over a linked list, and maybe even doing binary search on a linked list can begin to feel expensive. It can begin to feel slow. So much better is if you can move away from something that's linear, better than to move away from something that's even logarithmic, like binary search, toward this ideal of constant time lookups. So that's where we left off on Wednesday. We had linked lists, which solved a number of problems, but they introduced a number of problems. And sort of the goal at hand for today is to see if we can't create a data structure that's better than them all, for some definition of better, and gives us much faster performance. So imagine a structure like this. So what this is meant to represent is a table, quite literally, where there are indices into this table, and then there's also values that you can store at those indices. This is what's known in general as a hash table. And a hash table is a data structure that allows you to store pieces of data in memory, just like an array or a linked list might, but it allows you to insert elements into it and retrieve elements in it in, ideally, constant time. So imagine the following situation. Suppose that I need a data structure in which I can store any number that the user might provide between 0 and 25. All right. And I want to keep track of what values the user has typed in. All right, so I could certainly use this new linked list structure. And every time the user types in a number, I can, for instance, say the user typed in the number 1. The next time a user provides a number, maybe it's the number 9, I can then add a new node that stores the value 9. I can update my linked list. And now, henceforth, if I ask the question, has the user typed the number 9? How do I answer that? Right, my linked list presumably is represented by this pointer called first or whatever. So how do I answer a query of the form, has user typed 9 before? Traverse? Yeah, so traverse the list and find it. The running time of which is obviously big O of n, right? Linear time, in this case 2 steps, but that is in fact a linear time, and we can return true or false. All right, so that's linear time. And granted, short list, but imagine 100,000 such numbers, pretty slow, relatively speaking. So what's a better way of remembering what numbers a user has typed in if you can at least for now assume some bound on those numbers? As always, leading question here. All right, so what's smarter than this approach? Right? Clearly, linked lists are not the answer to all these problems. Yeah?
You know if it's within certain bounds, you can store the index of the value.
Yeah, so if you know it's within some range, why not just use an array which has this built-in feature of indices and just have a data structure that looks like this, that has presumably 25 different indices. Here's 0, 1, 2, and so forth. And when you initialize all these values, for instance, to 0, and then when the user does, in fact, type the number 1, what should you do with respect to this array? Yeah, you should just change the index 1 to be a 1. So use it essentially as a bit set, an array of bits, even though we're just using integers for conversation's sake. Next, if the user types in the number 9, well, somewhere out here, what was a 0 at location 9 instead becomes a 1. So what is the running time of inserting into this list? So big O of 1, right? You can immediately access it. There's the upside of random access. What about the running time of the find operation? Answering queries of the form, has user typed 9 before? All right, so it's also 1. So this actually seems to work quite well. But let's relax one assumption. Let's no longer assume that the user is going to type a number within a specified range, but rather they're simply going to type in some non-negative integer. That's the only assumption now we can make. What's the obvious problem with this data structure, given how we defined it? All right, so you clearly don't have enough buckets to remember all of these values. And this was a problem that some of you ran into, I believe, in the hacker edition of a recent problem set, where we asked you to sort not in big O of n squared time, but rather in linear time, which is sort of non-obvious perhaps at first glance. And unfortunately, in here, too, the implication of using this same data structure, if we just need to handle non-negative ints, is to have an array of what size? It's like 2 billion, maybe 4 billion if we're using an unsigned int. So, I mean, we can represent that with an int, but 4 billion, an array of length 4 billion takes up at least how much space? Right, we just need zeros or ones, but for simplicity, let's assume we're just using ints, right? Because we're thinking in terms of ints. So that's 4 billion cells in the array. Each int is, so that's 16 gigabytes of memory, just to answer queries of the form, has user typed this int in. So clearly not efficient, right? Once you relax that assumption, which we had to give you, those of you doing the hacker edition, of some bound, it becomes very problematic, at least given today's computational resources and real-world RAM implications. So what can we do? Well, what if I give you this assumption that realistically running this program, yeah, the user might type a number between 0 and 4 billion, but the numbers they provide are going to be sparse. That is, they're not going to type 4 billion or even a billion numbers over the life of this program, they might type in 20 numbers, 50 numbers, 100 numbers max. Well, let's start with that first scenario. If the user's only going to type in 20 values maximally, but each of those values can be anywhere in that range from 0 to 4 billion, can we still use this same idea? Yeah?
Take the log of the number and then have like a linked list coming off of the array.
Oh, OK. So that's interesting. So we can use take the log of the number the user types in to really rein it in and make it much smaller. So one catch with that, is that going to give us back ints necessarily? So there's maybe some rounding issues there that we might have to deal with, and that's fine. Let's come back to your linked list proposal, because there's actually a simpler way that we can constrain where we might put these things in this array. What's a more obvious approach, perhaps? Yeah, so remember the modulo operator, right? Anytime you've been worried about overstepping the bounds of your array, take it modulo size of the array. Right? You did this with Caesar. You've done this perhaps in other contexts, so that even if the user types in a bigger number than we have room for, suppose they type in 26, well, we can do the input number that the user types, or let's call it k that they type in, the key that they type in, mod n, which in this case is going to be 26. So if the user actually types in 26, and we do 26 mod 26, that gives us 0, the implication of which is we should actually change this bit to a 1 to signify that the user typed in the number 26. OK, so this is good in that we're at least able to remember henceforth that the user typed in 26, but there's obviously a problem. Yeah, so right, there's this ambiguity now. Did they type 0, or did they type 26, or did they type 52? And so forth, right? You have this possibility for collisions. OK, so now let's push harder on that idea, because now at least we have this ability to still do constant time lookups and constant time insertions, but there's this probabilistic risk that that's going to be a bad thing, right? We might actually collide. So what could we do instead? And let me clean this up to an initial starting state so we can start the story anew. So if this is our array, and just for clarity, I'm going to assume that there's zeros if there's nothing written there, just so we don't mess up the drawing too much. So now the user has typed in 26. So we set this bit to a 1, thereby signifying they typed 26. OK, what now can we do if the user subsequently types in 0 or 52, which is going to, in theory, give us the same location? OK.
So we can have one keep track of 0 to 26, the other one of how big the number was. Like
OK.
1 times 26 is 2 times 26 is 3 times 26, and we sort of make it like our normal computers. We have the 10 place and the 0.
OK. OK, and let me actually take that same spirit, but simplify it for a moment, and then take a bigger step in that direction. So one of the problems inherently now seems to be that all I'm using is a bit, a 1, to signify that something's there. But if we declared this array to contain ints, what might be marginally smarter to store there rather than just a yes/no answer, if we want to avoid this ambiguity? The exact value the user typed in, right? If we've already got ints to play with, why risk ambiguity when you can just store the number itself? OK, so now slightly better, right, in that there's less ambiguity, but there's still a problem. And we'll come back to Karen's suggestion in a moment. But what's now, to be clear, the problem? Right, now we can still just store this 1 value, right? If the user subsequently types in 52 or 0, that too is going to be problematic. All right, so what might we do next? And Karen's approach is nice. Let's take an even simpler approach, perhaps. And again, I'll point to this leading question, just so we sort of take steps upwards. Yeah?
Make an array out of, like, add another dimension to that array.
OK, so that could work well. We could actually just start hanging values off of this element, off of this cell, so that we essentially now have another list in this direction. And maybe this could grow, certainly. This could maybe just be initialized to be of size 100, just so that worst case, we can tolerate at least 100 numbers. And then worst case, if the user types in 101 numbers that happen to end up at that location, what do we have to do? Just recalling same kinds of problems we've seen before with dynamic memory. Yeah, just grow it, right? Double the size, throw away the old memory after copying those values into the new one, and there we have a pretty good structure. Well, just so that Not because this is the most intelligent solution, but just because it's worth noting, because it's not an uncommon solution. Let me make mention of what the term on this slide is suggesting. This idea of linear probing is actually not as good of a solution as you just proposed, but is, dare say, simpler, because you get away with using less memory. So one of the first approaches that a computer scientist might typically take to this problem in the interest of conserving memory and not using more RAM than is necessary is to simply do this. If you get a collision, so to speak, whereby you want to put multiple values at the same index in your array, well, you just start probing your array for an empty space, right? So if we actually want to insert 0 next, well, we end up here, we realize, darn, there's a number here already. Let me at least find the next available space. That ideally is not too far away. So you start probing all of the neighbors of this cell. And in this case, it turns out that the next cell is available right there. So I would just tuck 0 away there. All right, if next time the user types in 52, well, 52 mod 26 is also 0. Can't go there, so we probe a bit further. Still can't go there, and so we put it here. The nice thing about this is that if you assume like a uniform distribution of numbers, that is, there's no expected pattern, odds are this might not happen all that often. And even if it does, if the whole goal is to have this sparsely populated array, at least you're likely, statistically, to have a bit of buffer space surrounding that particular element. But theoretically and asymptotically, what is now the running time of insert and or find devolving back into? Big O of n, right? If you take this to the mental extreme of assuming that the array is almost filled, in the worst case, it's possible that the user types in some multiple of 26, but it's the last value they've ever typed, and just by chance, the only empty slot is way over there, so you have to probe the entire list. So then you get into these issues where the assumptions you've made and the types of data the user's providing start to influence really the real-world behavior of this data structure, but at least early on, it's quite efficient. Maybe its performance just evolves over time, but again, that's sort of a design decision as to whether or not that's acceptable. And in fact, we can certainly do better than that potentially than linear probing, and some of these ideas have already been offered. But let's try to capture just for a moment the odds with which this happens. All right, so this is actually representative of this cute little problem typically called the birthday problem, which stated in terms of CS50, in a room full of n CS50 students, where n today is small, what's the probability that at least 2 students share the same birthday? So what's this getting at? Well, if we assume a uniform distribution of baby making throughout the 12 months of the year, you have equal probability that any given day of the year might be someone's birthday. That's sort of the same idea here. If we here are at least framing it not in terms of 365 or 366 days, but just 26 different possible elements, if you're assuming random numbers being inserted into this data structure, it's sort of the same question. What is the probability that 2 numbers taken by chance are going to want to end up at the same value? And I'm going to start tossing a verb out here. When I've said that you compute k mod 26 to determine where this element should go in the array, the verb a computer scientist would typically use there is hash the value k into the array. So if I say, where does 26 hash into? Well, that hashes to 0. So that's sort of the jargon we would use here. So consider this problem here. If there are n students in the room, what's the probability that any 2 of you happen to have the same birthday? In other words, if we try to declare an array of size 365, assuming no leap years, and we just plopped all of your birthdays into that array, how likely is it that at least 2 of you would be put into the same bucket, that is, put into the same cell? Well, how do we go about answering that? Like, what is the probability of a collision, so to speak? And don't turn the page to the next set of slides, since it'll spoil the fun. Yeah? Yeah, so actually, often when you find yourself hesitating as to solve some probability question, it often means that it's hard to solve it in a sort of positive sense, to actually compute the real probability. Sometimes it's easier to compute the opposite. What's the probability that no one in the room has the same birthday as anyone else? And then just subtract that value from 1 and sort of flip the answer around. Well, if we consider, just for discussion's sake, the first person in the room. Well, what's the probability that the first person in the room, say Emily, has the same birthday as anyone else? Well, if she's the first student under consideration, don't worry, you can go back to working. What's the probability? Well, Emily can have her birthday be any of the 365 days out of the year, and there's 365 days out of the year, so it's perfect. It's 100% sure that she does not have the same birthday as anyone else. Okay, what about the next person in the room? Well, unfortunately, Emily has just consumed one of the possible birthdays. So the probability that the next student does not give us the same birthday as Emily's is going to be 364 divided by 365. Right? It's a slightly lower probability because there's that one day that's going to give us a collision. For the third student in the room, this probability becomes this. And again, we're looking at the product here. What's the probability that no one in the room has the same birthday? That's the equivalent to saying that everyone has a different birthday, which is further equivalent to saying this student can have any birthday, this student can have any of 364 birthdays, this student can have any of 363 birthdays, and so forth. So if we do this ... all the way down to n, it works out to be that formula all the way on the right-hand side, which if you start plugging values into it, it turns out that a collision is pretty darn likely. Odds are, if we were to spend time doing a poll of hands here as to who has a birthday in January, January 1, January 2, and so forth, odds are, even with a room of this size today, we would probably find at least 2 of you having the same birthday. This neat little applet someone whipped up, really just to compute this formula, kind of lets us see this. So this little application here asks us to enter number of birthdays to calculate. It's going to generate n pseudo-random birthdays from all the days of the year. So if I type in 10 and hit enter, what it just did, using a bit of Java, is generate 10 different birthdays. Looks like there's no collision. So the implication is that if we have an array of size 365 and I choose 10 pseudo-random numbers and I hash them into that array, doing k mod 365, odds are, according to this very unrepresentative individual sample, is we're not going to get a collision. But if I do this a lot, pretty much 10 students out of 365 possible days, you're not likely to get a collision, at least very likely. Well, let's bump that up to 20 students. All right, so already, and granted, we're not doing a very rigorous sampling here, with 20 students, it looks like it's more probable that we're going to have a collision. I'll run it once more. Still one date. Once more. Now we have 2 dates. So already with just 20 students in the room, it seems that a collision of birthdays is pretty likely. Let's bump it up to 30. So 30 by chance, there was none, 1. So there's no pattern that's necessarily obvious yet. Let's go up to 40. So it's still pretty likely. 50 students. Now it's pretty much guaranteed that we're going to have at least one collision, because notice, out of all those hitting enters, I only saw one instance in which there was no duplications. And then obviously, to make clear, if I choose 365, well, we're going to start having a lot of collisions. But that's a lot, too. Like 93 collisions out of the whole year is pretty high. Well, if you actually plot this thing and just run that simulation a lot, what you see is that by the time you hit, let's see, about looks like 40 students in a classroom, the odds of 2 people having the same birthday is over 90%. Okay, now it's kind of an interesting question just in general in real world terms, but the implications for our data structure is that we can't just cross our fingers that 2 values are not going to hash to the same location, because according to this simulation, odds are that's very, very likely, which means we need to do better. We can't just allow these collisions to happen if the goal at the end of the day is to have better performance. So I think what Karen was, similar to what Karen was getting at, is that we can enhance our data structure to remember not only values like numbers, or in this case, people's names, but we can also maintain, we can also do the following. Actually, this isn't quite like what Karen was suggesting, but rather this. So if the problem a moment ago, where'd it go? All right. No, it's not there either. I guess it's been erased. All right, so the problem a moment ago was that with linear probing, we're simply looking for the next available location to actually store the value that's been typed in an int when we did it on the board, maybe in this case as a string. That's stupid, because what's then the running time of the find operation subsequently? Just to reiterate. So it's potentially linear. I mean, it is asymptotically linear. Worst case, you might have to traverse the whole list. That's pretty dumb, because didn't you already, to insert that element, traverse the list looking for the first available hole? So an obvious marginal improvement on that approach is to actually remember, by way of one of these pointers perhaps, where you actually put that value, so that you can skip over all of the elements that were not the value you're looking for. Right? If I recall, the picture that we did, actually here it is. So the picture that we did earlier, when I tried to insert 52, it didn't belong, it couldn't fit here, it couldn't fit here, but it could fit here. But notice then, to find that value subsequently, I need to look here, here, and here. But I could skip this element if I just kept around a bit of a reminder as to where I put it. In other words, if I kept around a pointer from here, essentially, to the actual location. And the spirit of what's called coalesced chaining is that you still probe for an available value, but you cache the location of where you actually dumped that value. And in this case, this is a bit of an oversimplification, because if these values all hash to the same value, the spirit of this chaining idea is actually to say, well, this guy ends up here, and then you continue the chain. If the next value also belongs here, and ideally also belongs here, well, unfortunately, this hasn't made much of an improvement. But for longer examples, like this diagram here from a data structures book is suggesting, once you actually start having lots of different values being plugged into your table, the idea of remembering where you put them by way of these pointers can be quite advantageous. Not asymptotically, for those following closely, but at least in real-world performance, it allows you, in theory, to start skipping through the array more quickly. But let's not dwell on this, because there's a better solution arguably yet, which is what you proposed earlier, which is generally known as separate chaining. Right? We've had all these new tools in our toolkit, so to speak, over the past week with all these different data structures. Once you start having all of those building blocks, can you start joining them in to make ideally the most intelligent solution possible? So what this picture depicts is perhaps the most common approach to a hash table, which is to say you do have an array typically of indices, the locations to which your elements should be hashed. But you don't store the actual data you're trying to put into this data structure in the array, but rather you hang the data off that array by way of a linked list. For a couple of reasons. One, it's dynamic, so you're not wasting memory unnecessarily, and it can grow arbitrarily. And two, again, you can make this assumption that if your hash function, so to speak, and in this case, my function is as simple as modulo, the thing that's manipulating the key, is a good one, ideally you'll have a uniform distribution throughout your hash table, by which I just mean that none of these chains will end up being terribly long. Right? If you assume a uniform distribution of inputs to this table, even though they will, according to the birthday problem, inevitably hash to the same location over time, ideally none of these chains, so to speak, will be terribly longer than any other. And that's sort of the best you can hope for, is that the running time of your lookups and inserts, no matter what value it is going to be predictably around the same performance. All right, so let's ask this question now. What is now the running time of insert into a hash table that's designed like this? We're assumed for simplicity that each of these individuals whose names we've stored in this hash table had an ID number, perhaps. And that's how we figured out what index to put them in, what chain to put them in. So what's the running time asymptotically of insert into a hash table that looks like this? So it is, in fact, still n. Right? And here's sort of the problem when you start thinking about asymptotic notation. In the worst case, if because of bad timing, a bad sequence of inputs, a bad collection of students who just all happen to have the same birthdays, one of these chains, in theory, could be how long? Right? So n, which suggests either that your data, you made wrong assumptions about it, or two, your hash function is just wrong. Right? Another hash function you could use besides k mod 26, just to be sort of silly about it, would be to say that the hash value of k, so call it h of k, just equals 0. Right? What that means is no matter what the key is, always put the data that you're trying to store at index 0. All right, stupid hash function, especially if your table's larger than that, as in this case, a length 31. But what it illustrates is that the chain, in theory, could get terribly, terribly long. But ideally, if you have a uniform distribution of numbers, or at least your hash function is better, and by that I mean it gives you a better distribution of numbers, forget about asymptotic notation and think in real terms. What's the running time going to be of insert, ideally? Not necessarily n, the number of elements in the list, but introduce verbally some other variable with which we can express in real-world terms the running time of insert or find. So n elements, if they all get hashed nicely such that none of the chains is really longer than any other, what's that? 26, right? Or if we generalize it, let's call it m. So if n is the number of things you're putting in the table, and m is the number of buckets that you're allowing yourself, then the size of your array, ideally none of these chains should be longer than n over m. Now again, asymptotically, not a big deal, because this is a constant, and we almost always cross that out and just talk in terms of big O, of whatever the highest term is. But in real-world terms, and for a spell checker, for instance, the milliseconds start to matter, and the actual real-world performance matters. That might be OK. Because does this data structure now have any bounds on how many elements it can store, unlike an array? So no, it can sort of grow forever. And so the fun or the challenge really of problem set 5, for instance, is going to be in part to figure out what data structure to use to store hundreds of thousands of words in memory simultaneously and optimize the lookup time. I mean, in reality, we could have truly constant time for a hash table. And think back to our first example today. If you wanted truly constant lookup times for ints, for non-negative integers, what price does that come at? RAM, 16 gigabytes of RAM. And maybe that's OK. But if that's not realistic, you begin to have to make trade-offs. And again, here's that theme again. There's this balancing act between space and CPU time and developer time and complexity that ultimately revolve around design decisions. Yeah?
If all 200 of us decide to use 16 gigabytes on night simultaneously, what would happen?
That's a good question. So if all of you choose to implement constant time hash tables by just giving every string its own bucket or every int its own bucket, NICE won't let you allocate that much RAM. I think it'll bound you at 1 or 2 gigs maximally. And even then, it won't be real RAM. It will rather be virtual memory, which is just the use of hard disk space as though it were RAM, which means all of your programs, even if they're allowed to run, will run terribly slowly. And actually, if you've never done this before, we can actually ask ourselves the questions by typing cat proc. If we type CPU info there, so you can actually look at the specs of a Linux machine, usually with this command. So what this is suggesting is that processor number 0 is an Intel processor. It runs at what speed? Yeah, so just under 3 gigahertz. So that's pretty good. Looks like it's got, let's see, this isn't memory information, but it seems to have another CPU, numbered 1, a third CPU, a fourth CPU. So this is a quad CPU machine. So that's actually pretty good. And remember that NICE is a cluster. So there's multiple machines like this. And usually if we type mem info instead of CPU info with that kind of command, we start to see how much memory these things have. And this suggests what? The total amount of memory. Yeah, so let's do your bytes and kilobytes things here. OK, we'll write it off at a lot of memory. OK, and forget all these other values. They're more machine configuration specific. But there's a good amount of RAM, but certainly not enough for 16 gigs or even 2 gigs per person. It's all shared resources. OK, so just to take one step back, let's make clear the following. If your things that you're storing in a hash table don't have integral values, but rather are strings, which frankly is going to be the case when we're implementing a spell checker, how in the world do you figure out where to put these things in the first place if you're hashing strings as opposed to ints? Or maybe even more generally, or more specifically, if you're trying to put student objects into a hash table, you could use their ID number. But what if the students don't have ID numbers and they're just strings of names and houses, or in this case, just people's names? Well, what can you do if you want to store non-numbers in a hash table? Yeah?
Can you use the ASCII value of the first letter of your name?
So that's pretty clever. And in fact, that's what I think, let's see, is this one getting at? So this one's not getting at that because it seems to be more random than that. But that's a pretty good one, right? If you're storing names, and if we assume, maybe naively, that all letters of the alphabet are equally likely to begin a human's name, well, then we can just look at the first character of someone's name, and we can convert it, say, to uppercase, just so we normalize everything, subtract off the number 65, and what does that give us? A number between 0 and 25, which is perfect for hashing into an array or into a hash table. And there, too, is one of the design decisions you'll have to think about for problem set 5, which is what hash function to use to optimize the performance of your dictionary. If you just use the first letter, that might not be such a wise idea, because odds are there's a lot more words that start with A, I would imagine, than say Q or certain other letters, which means if you're storing a hash table that looks like this, you're going to have a very long chain for A, potentially, if you use this data structure, versus a very short chain for Q, which probably isn't the best use of resources. Maybe. But there, too, there are trade-offs. So just to give you a sense of some other types of data structures, let me make mention of at least 2 others. So there is this variant of this idea of linked lists, which is to store not things linearly or laterally conceptually, but rather to allow a data structure to start branching for various reasons. And the depiction of that is essentially in the form of a tree. So trees, or binary search trees, are data structures that are commonly used to store data in a tree fashion. And as the name binary search tree implies, what that means, a tree, each of whose nodes each has just 2 children. And we'll revisit this issue when we get to problem set 6 and look at what's called Huffman coding, which will use trees. But suffice it to say for now that when you start using a data structure like a tree, well, it's much shorter pictorially than, say, a linked list is long. In other words, you can group more data together higher up, which ultimately tends to give us logarithmic performance. But we'll come back to that. But let's conclude with a look at this data structure, which is perhaps the most sophisticated of them and is particularly a juicy opportunity to implement for problem set 5, but does come at a cost. So it turns out that this data structure, called a trie, short for retrieval, but pronounced trie, is meant to be a play on words of tree, essentially allows you to implement lookups in a hash table, not in big O of n, or even big O of n over m, but big O of, we'll call it k, for lack, well, we used k before, let's call it L. So big O of L, where L is the length of the string that you're storing in the data structure. Okay, so that's actually pretty good, because if you're trying to implement a dictionary, which contain English words, most English words are relatively short, 5 characters, 6, 7, 8, and rarely gets terribly longer than that, and even if it does, it's pretty rare. So L equals 5 or 6 or 7 or 8 is certainly longer or shorter than n equals 100,000. In other words, that's much shorter, quicker in terms of the performance. So how do you actually look up a name, a word, and store a word using time that's proportional only to the length of that piece of data, as opposed to the size of the data set into which you're inserting it? Well, you can use this data structure known as a trie. And essentially, and this is really just a teaser for problem set 5, you implement a tree, each of whose nodes is an array of size 26, where each index obviously represents a letter of the alphabet. And if you want to store the word dog in your trie, what you essentially do is the following. In the so-called root node of your tree, which looks like this and again has 26 different elements, this is going to represent A, B, C, and D's here, and so forth. What you do to store the word dog in this data structure is you put at location D a pointer to yet another array of size 26. So it looks in memory a little something like this. And then in this array of size 26, you put a pointer at location O, to take a guess, another node that is also an array of size 26. And then finally, at location G in this array, you need to store some kind of special value to actually indicate that this is the terminus of this little chain that you've built. So that is ultimately a design decision for those of you who adopt this data structure for problem set 5. But notice the implication if we continue this logic. If now we're using this data structure of just storing an array for each node and using pointers to sort of show us what paths to valid words exist in this data structure, how much time does it take to look up a value in this tree? Well, for the word dog, it takes us one operation to find the D pointer, one operation to get to the next array, one more operation to get to the final array, and that gives us 3 steps. Even if this data structure has 100,000 other words stored in it. Okay, but nothing comes for free. This almost sounds too good to be true. If you followed at least the design of the structure, what's the cost of this thing? All right, so memory starts to become an issue. Plus, there's a bit of ambiguity potentially. What if, and suppose that we also wanted to store not dog, but dogma. You also have to figure out how to contain strings that are substrings of other strings. And there are ways around this, because presumably, not only do we want to remember that a word ends there at the G, but we also want to remember that this thing also leads to another array that happens to map to an M, which in turn leads to yet another one, which happens to lead to an A, and so forth. So there's some really juicy opportunities for design decisions there. At the end of the day, though, it's unclear if this data structure in reality will be faster than something like this. So know that for problem set 5, which we'll distribute next week, this is perhaps a reasonable starting point for any such dictionary. If you're interested in pushing the limits of your comfort zone a bit, this is a fun one to try implementing as well, because it offers these interesting design opportunities. With that said, we'll see you on Monday.